Okay, this is the continue on a little bit with Darkens Formalism and the Wagner's Formalism. This is the thing on the website. I think it's number 10, the paper here. Take a look at. Just to recap a little bit, Darkens Formalism. Let's take, for example, a liquid phase, and we'd have here CaO, I'm talking about a liquid. There's in the phase diagram, there's a two liquid region here. If you're up here, say a temperature, the liquid is completely, this is the phase diagram, the liquid is completely miscible in all compositions. But there are many systems in which, for example, in this case, the whole region around here is quite ionic. Calcium oxide is ionic, and the silica goes into the ionic liquid. We'll talk later about slides, but it's a orthosilicate. And over here you have a sort of a very different polymeric structure of a polymeric silicate network. So you have sort of a local structure over here and another sort of different local structure over here, and then of course there's a transition region where the two structures come in together. And because of this, you actually have two liquid regions at low temperatures. Rather than have this transition region, which is kind of hard to fit everything together, the system at lower temperatures simply prefers to split into two phases, one which has one sort of structure and the other has the other. But as you go to high temperatures, above the critical point, you do have a complete liquid solution. Now, if you're going to treat this thing with the Gibbs energy equation, going from CaO to SiO2, you have to treat it with one. It would be nice to be able to treat it this way. This would be G naught of the liquid SiO2, and this over here is G naught of liquid CaO. This point up here is some sort of a hypothetical G naught for SiO2 with a calcium oxide structure. And this is sort of some sort of a hypothetical G naught of calcium oxide with a silicate structure. So let's call this area L1 and call this area L2. So this would be the curve for L1 and this would be the curve for L2. Okay, and this would fit kind of nicely in the idea that this is a liquid, this L1 is a liquid between real calcium oxide and some sort of hypothetical ionic silica. And this L1 equation can then be given by, for L1 you would say the excess Gibbs energy of L1 would be constant times X silica, say C1 times X silica, plus a constant times X1, X2. So it's a regular solution, whereas this distance here is then C1. This is just as treating it as we did when you have two different phases, standard cubic and hexagonal, like in figure 22 and so on. And this equation then, this C then, it corrects for the standard state from silica liquid to this hypothetical silica liquid, and that's the equation of this line here. And that's the plus a regular solution term. And we will find that this equation fits quite nicely over this region over here. Meantime, over the L2 region, for the L2 we would have a similar equation. Gxs of L2 would be another constant times the mole fraction of CaO plus another omega times X1, X2. And that's a very simple equation that would apply quite nicely over this region, because where that structure stays more or less constant. And this would then be consonant with the idea that you have sort of one liquid with one local structure and another liquid with another local structure. Okay, but the trouble with this, of course, is that these don't meet in the middle. Or another way of looking at it, what if we use this equation here? You know that Gxs has to, it's all one phase, the liquid is one phase. Gxs, of course, has to be 0 at both ends. But obviously this equation here, when x silica equals 1, it's not 0, it's equal to C1. Okay, so the Gxs is not, of this phase, is not 0 at this end, it's up here. Okay, so this equation clearly cannot apply over the entire composition region unless C1 equals 0. Okay, and similarly this equation has to go to 0 over here, but it doesn't, because when X calcium oxide is 1, it's equal to C2. This distance here is C2, all right? So you can't do it. So if you want these equations to apply over the whole range, C1 has to be equal to C2 equal to 0, and omega 1 is equal to omega 2, and you get a regular solution. Okay, and you can't fit it quite as well. That's what we're stuck with doing. If the things ever are miscible like this, to have the same structure, we pretty well have to do that. Otherwise, we would run into trouble. Up here, we couldn't express the whole thing by one equation, and we need one equation for a single phase. So, and even if in the binary system we may never have complete miscibility, you might very well in the ternary system, which involves this binary, and then you'd be in trouble if you had a different standard state. Okay, so we're not going to be using Darkins. This is called Darkins Quadratic Formalism. Darkin back in the 1960s. But he showed there are an awful lot of many systems, mainly liquids, that obey this kind of thing that I showed you the other day, silver chloride, silver sulfide. There's a very narrow transition region, and to express each terminal region with these two equations, you can get a very simple fit with just two parameters on either end, a beautiful fit, indicated there really is something physically correct about the model. Unfortunately, it doesn't apply over the entire composition. Anyway, so that's Darkens Formalism, which I'm presenting here to show you a bit more about, not that we're going to be using Darkens Formalism, or you'll be using it mathematically, but it shows you something about the structure of materials. Now this is also, I had it here for liquid. The same thing would be for a phase, say an FCC phase. If these are two different structures, if this was FCC and this is HCP, then in fact, of course, you can do it this way because they're not the same phase. They don't have to meet in the middle. But if they're the same phase, FCC, then you really shouldn't do it this way. But even then, for a phase like a solid phase, you say, well, now it is the same structure on both ends. Okay, it's both FCC, but they're different lattice parameters, they may be different bonding types. It really is two sort of different solutions. But this has mainly been used for liquids. Okay, now there is another. So much for Darkens Formalism. Now there's Wagner's Formalism. Carl Wagner for dilute solutions. This was developed by Carl Wagner about 1950. Carl Wagner being one of the top thermodynamicists or metallurgists of the last century. And this was for dilute solutions of a component. Okay, so this is for a dilute. He's dealing only with a solution that's dilute over here. Okay, so in fact you could use something like this because you're only applying it over a composition region that's rich in one component. Okay, that's all he intended to apply it to. Okay, so now for Wagner's formalism. Okay, we're talking now about, so we're dealing now with just this L1 phase. We know that this is the G naught over here, but we're dealing with the phase that goes up to here. We call this component 1 as the solvent, and component 2 will be the solute. All right, can I write over there, Jenny? Okay, so we're dealing with the solution. Okay, so a 1 equals solvent, so x1 is of the order of 1. And the solutes are, for the moment, the solute is component number 2. So if you have an ideal solution, then log gamma 2 is equal to 0. The solution's ideal. Okay. The next thing, though, would be you have a Henryan solution. So log gamma 2 is log gamma 2 0, which is the limiting value. Gamma 2 value equals gamma 2 when x1 equals 1. Okay, the limiting value, that's a Henry's law, a constant activity coefficient. Okay, now Wagner said, well, if you're going to somewhat less, and now you can deal with other solutes. We're not talking now just about a binary. We can have 3, 4, 5 components. So you could have, I'm sorry, is it better on this side? Log gamma 3 would equal to log gamma 3 0, and so on. Okay, so that would be, you're dealing with a solution that's very dilute, so it's very rich in component 1. It's very rich in component 1. But log gamma 2 0, log gamma 3 0 are the limiting values of the Henryan activity coefficients when x1 equals 1. Okay, so this is an extremely dilute solution. So Wagner said, okay, and there's experimental evidence for this as well, and this has been used a great deal, but was used and still is used a lot by metallurgists. We don't use it particularly in, say, CalFad type things, but you're going to come across this, so this is a little bit different from Darkin. He said, okay, you're going to a solution that's not extremely dilute, but it's somewhat dilute. In that case, he brought in corrections. So he said, well, log gamma 2 now is equal to its value at the limit when x1 equals 0, plus it's equal to a constant, and what do I use here? X epsilon 1, 2 times x2 plus epsilon 1, 3 times x3, etc., where epsilons are Wagner's linear activity coefficient. They're called Wagner's interaction parameters or interaction coefficients. So log gamma 2 is equal to its limiting value, and it depends linearly on the mole fractions of the various solids. So this epsilon 1, 2 is called a self-interaction coefficient. It indicates how the fact that x2 is around affects log gamma 2. Epsilon 1, 3 is a cross-interaction coefficient. It shows how the presence of 3 affects the... Okay, now clearly when the system becomes very dilute, x2, x3 all go to 0, and this is the limiting case. Okay, and this is just a first order correction. So this is Wagner, where similarly log gamma 3 plus epsilon 1, 3, x3 plus epsilon 2, 3, what am I reading here? 1, 2, 1, 3. I2. Sorry, I'm wrong, that's what I'm asking. Of course, it's not 1. 1 is the solvent. This is epsilon 2, 2. This is epsilon 2, 3. This is the effect of 2 upon the log gamma of component 2. Epsilon 2, 3 is the effect of 3 upon the activity coefficient of component 2. This then would be epsilon 3, 2, x2 plus epsilon 3, 3, x3, and so on. And you can do that for all the solutes. So that's Wagner's interaction parameter formalism. Okay, this is simply saying that in the infinite dilution, of course, every component, infinite dilution, you have a huge amount of component 1, and every time you add an atom of 2, it finds itself completely in an environment of component 1. So you have a constant activity coefficient. But as you add more and more 2, there's a possibility of finding a 2 next to another 2, and then that then gives you the influence of this. So x2 is that probability, and epsilon 2, 2 is your, so you have the self and cross interaction parameters. And this was proposed by Wagner as applying at infinite dilution, applying for dilute solutions, not infinitely dilute. Okay, that's called Wagner's first order. First order because you're just going to epsilon x2 to the 1 power. So that's Wagner's first order interaction parameter formalism. Now the question is for log where, okay, so there it is up here, where gamma I is the activity coefficient, where from the Gibbs, okay, the Gibbs-Duhem equation, we'll talk about that in about 5 minutes, but the Gibbs-Duhem equation is a thermodynamic necessity, and the Gibbs-Duhem equation will, as you see in a minute, if you don't already know it, is the sigma xi d log gamma I must be 0. So x1 d log gamma 1 plus x2 d log gamma 2 has to equal 0. If you apply that expression to that equation, you'll see that epsilon ij has to equal epsilon ji. In other words, epsilon 2, 3 has to equal epsilon 3, 2. The effect of 3 upon the activity coefficient of 2 must be the same as the effect of 2 on the activity coefficient of 3. That's a thermodynamic necessity. Okay, so that can be proven. Plus, you can integrate the whole thing, and you can obtain the expression for the activity coefficient of the solvent. Okay, if the epsilons are all 0, then of course the solvent obeys Raoult's law, log gamma 1 equals 0. If it doesn't, you can apply Gibbs-Duhem equation, and you can prove that this is the, so you can see when x1 and x2 are 0, log gamma 1 equals 0. But when you deal with it, of course, if the thing is not ideal, if it remains Henryan, actually, if the epsilons are 0, then log gamma 1 is 0 everywhere, but with the epsilons in, you get deviations from Raoult's law. This, however, when you derive this equation, when you do the derivative of this, when you derive this equation from these, you have these equations up here, and you use the Gibbs-Duhem equation, and you end up getting this equation. You are making the assumption when you do that x1 equals 1. So this equation really only applies at infinite dilution. And you can show that if you take this equation and these equations and put them into the Gibbs-Duhem equation at other than infinite dilution, they don't satisfy it. In other words, Wagner's interaction parameter formalism is inconsistent with thermodynamics at anything other than infinite dilution. It's not bad. It's only a small deviation, but it isn't quite right. And the further away you get from infinite dilution, the worse you get. Or you can also show that Wagner's just looking at these equations, they do not obey this expression, d log gamma I dnj has to equal d log gamma j dni. And why does that expression have to be obeyed? That's simply taking the second derivative. If you take mu1 is equal to dg dn1, mu2 equals dg dn2. Okay, d squared g dn1 dn2 must be equal to d squared g dn2 dn1. In other words, the order of differentiation doesn't matter, the second derivative. D squared g dn1 dn2 is the same as d squared g dn2 dn1. So you put that back into here and you find that dg, the d mu1 dn2 must be equal to d mu2 dn1. You put mu2 is RT log activity plus RT log gamma, and you end up with that expression. Okay, the order of second differentiation doesn't matter, so d mu1 dn2 has to equal to mu2 dn1, and you end up with that expression. And if you take this expression and you put in Wagner's formalism for log gamma 1 and log gamma 2, it doesn't work, except at infinite dilution when x1 equals 1. Okay, so Wagner's formalism is used with the recognition of this problem, meaning the further away you get from infinite dilution, the worse the formalism is. And it's not just that the log gamma solvent doesn't work, it's actually that, forgetting that, you don't care about a log gamma solvent, it's just that the expression, those two expressions for log gamma 2 and log gamma 3, independently of what you write for log gamma solvent, are not consistent with this relationship number 7. Okay, so even for the two, log gamma 2 and log gamma 3, except at infinite dilution, are not consistent with a necessary thermodynamic relationship. It isn't too bad as you're close to infinite dilution, but the further away you get, you're doing something that isn't quite right. Or putting it differently, if over a certain composition range you fit up log gamma 2 to this equation, then thermodynamically log gamma 3 cannot obey that equation exactly. Now, there have been many things written about how to solve this problem, and they call it a paradox. There's no paradox. And it's actually really, the way to solve it is really just look right here. This was Darkens formalism. GXS, this is Darkens formalism for the dilute solution, which I wrote on the board before. Okay, in Darkens formalism you have GXS equals constant times x2 plus a constant alpha 1. This is what I called omega before. All right, 1, remember, is the solvent. Okay, so this is Darkens formalism, which I just had on the board a minute ago, for a solution which is dilute in component 2. Okay, the XS is the, okay, if the C is 0, then it's a ring idea. So this is Darkens formalism for a solution that is dilute in component 2. Okay, if you take that's the formalism for the excess integral property, GXS. If I differentiate that to get the partial property, the corresponding partial property for component, you can do the differentiation yourself. Start with that. That's the integral property, that is GXS. And you want to get GXS of component 2. You can calculate that out yourself. You know how to do that now. It's equation 92 from the book, chapter. And what you will get, GXS2 is RT log gamma 2. And what you will get if you differentiate this expression here, in order to get the corresponding expression for log gamma 2, is you get log gamma 2 is the constant alpha 1, 2 times x1 squared plus c2. Okay, that is Darkens quadratic formalism, based simply on differentiating this. Now, just to take a look at that, remember, Darkens quadratic formalism is the same as the regular solution theory when C2 equals 0. Okay, if I take C2 to be 0 up here, then I simply have the regular solution theory. And of course, that's what we get. Take C2 to be 0 here. GXS is alpha 1, 2, x1, x2, and log gamma 2 is alpha 1, 2 times x1 squared, which you should know from regular solution theory. Okay, if the integral property is x1, x2 times a constant, then log gamma 2 is the same constant times x1 squared. Okay, or let's say that this term alpha 1, 2 is 0. If alpha 1, 2 is 0, then Darkens formalism is simply Henry's law. GXS is a constant times x2. And in that case, log gamma 2 is constant, which is the Henry activity coefficient. Okay, so if alpha 1, 2 is 0, this is Henry's law. If C2 is 0, it's regular solution, otherwise it's Darkens formalism. Okay, so now we know that Darkens formalism is consistent with with the equations of thermodynamics. It is consistent with the Gibbs-Duhem equation, and if you take Darkens formalism and you put it into this this thing up here, it also works accordingly. It has to work, you see, because you're starting with the integral property. You start with the integral property, you're differentiating to get the partial properties, it's got to be correct. The trouble with Darkin is he started with the partial properties. He hypothesized, he says log gamma 1 is this, log gamma 2 is this, log gamma 3 is this, so he's forcing them into equations which he wasn't supposed to do because he started with the partial properties. If you start with an integral expression, it's got to be consistent. So this is consistent with thermodynamics. Okay, so let's write this out then. Let's expand x1 squared is 1 minus, okay, so there's your Darkens quadratic formalism. And let's expand that in terms of, simply replace x1 by 1 minus x2. x1, remember, is close to 1. 1 minus x2, you expand it in terms of 1 minus x2, and you get this expression here for log gamma 2. Okay, so now let's compare that to Wagner's formalism. This alpha 1, 2 plus C2 is a constant, so that's your log gamma 2, 0. This second term, 2 alpha 1, 2 times x2, that's also a constant, so that's your term epsilon 2, 2. And this is the term here, alpha 1, 2 x2 squared, which makes Wagner's formalism consistent with proper thermodynamics. In other words, if Wagner had taken, so I'm Wagner took epsilon 2, 2, this should be, rather than writing x2 here, had Wagner written x2 minus x2 squared, then it's correct. It's the same coefficient, you see, alpha 1, 2, here's the same alpha. You're not introducing more coefficients. Darkens quadratic formalism has two constants. Constant term, a linear term, and a quadratic term, but the linear term, it's x1, 2 over 2. Okay, but the coefficient of the quadratic term is simply minus 1/2 the coefficient of the linear term. You see what I'm... Okay, so Darkens quadratic formalism, if you truncate this term here, is the same as Wagner's formalism, a constant plus epsilon times x2. Let's just do this for a binary system, forget component 3. Just do it for a binary system for the moment. And the thing's going to be first. Where to go? This is Wagner's formalism for the binary system. Okay? If you take that, you say epsilon 2, 2, x2 squared over 2, you've not introduced any more coefficients. And now this equation is the same form as this. This is the constant log gamma naught minus 2 alpha 1, 2 is epsilon 2, 2, and this is epsilon 2, 2. Okay, so this equation is the same as Darkens formalism. Now you can see if you truncate this last term, in other words, if you don't put this in, then that's Darkens formalism. And of course this is true. You can see now as x2 goes to 0, x2 squared goes to 0 even faster. So as you're dealing with a small range around the pure solvent, this term, x2 term, is much bigger than this term, so you can reasonably neglect this term. Okay, but if you're getting to more concentrated solutions, it's the neglect this term should be put in. But you don't introduce any more parameters by doing that. It's still a 2-parameter equation. This is a 2-parameter equation. There may be 3 terms, but there's only 2 parameters. Okay, so this then suggests very quickly a very simple fix for Wagner's equation. You don't have to rewrite anything differently. You simply say that in Wagner's equation you take exactly the same coefficients that Wagner used, the epsilons, but you simply say, instead of saying x2, you say x2 minus x2 squared over 2. And then you got it. And when you go to ternary systems, we can show again the ternary term epsilon 2, 3 should be x3, and I can't remember what it was now, but there should be a term that you add on to that. I cannot remember it. Anyway, the epsilon 2, 3 is the same thing. You can put a fix-up, you can read the paper, put a fix-up term in here, and it works. So you see, again, all these fix-up terms are quadratic terms, which go to 0 quickly as you approach x1 equals 1. So you can see why Wagner's formalism applies. This is some sort of a term, x2, x3, I can't remember over 2 something. Okay. But again, it's the same thing. These are quadratic terms. Okay, so this then, and the nice thing about this was, I mean, Chris Bale and I proposed this years ago. You can fix up most of these Darkens formalism parameters, the epsilons, were obtained experimentally. You can find tables and tables of these Wagner parameters, epsilon, in the literature. And many of them were obtained at very dilute solutions where, in fact, that's a reasonable assumption. So you can still use exactly the same numerical values of those parameters that you find in the tables, but you just add this correction term so that you can extrapolate further and make the thing consistent with the Gibbs-Doom expression. Although you do have to be careful, because sometimes the epsilons that you will find in the literature that were fitted to experimental data were fitted over a fairly large composition region in which this term should have been included, but they fitted it up to the equation without that term. So you get a better fit if you fitted it up to. Okay, and I showed a couple of things here. You can see this is the iron-nickel solutions. These are iron-nickel. So these are nickel solutions where iron now is the dilute component. And if you going down to infinite dilution, Wagner's formalism follows this line here. So you see the limiting slope is of course the same. The dashed line, okay, this is the line where this epsilon 2, this was 2.7, so that's the first term. This is the same term, 2.7 x minus x squared over 2. So of course the two come in to be the same as x approaches 0, but as x deviates from 0, this follows the experimental points and Wagner's line goes off. Okay, now as I said, many of these interaction parameters were determined only by these limiting slopes. In that case you're okay. You have the limiting slope is the same, so you get the 2.7 from the limiting slope, and then this additional term, quadratic term, permits you to have a proper extrapolation. Unfortunately, some of these things, as I say, were fitted in the literature in which they tried to fit a straight line through the points. Okay, in that case they got the wrong epsilon. You have to redo it. Okay, so Chris and I dubbed this the unified interaction parameter formalism, which brings together Darkens formalism and Wagner's formalism and corrects Wagner's formalism in a very simple way. And now that expression actually in that term turns out then in that case too, the expression for, now when you put in these correction terms, then this expression for the log gamma solvent is exactly correct thermodynamically. So when you make these corrections that we did, this equation is exact, the Gibbs-Doom equation is satisfied, and this necessary relationship is also satisfied. It's consistent with Wagner in the infinite dilution, it's consistent with Darkens formalism in less than infinite dilution, and it kind of explains what the problem was. Anyway, so when you see Wagner's formalism, remember these problems. And in the FactSage database, model type number 2 is the interaction parameter formalism. So you can use the interaction parameter formalism in the FactSage database for dilute solutions. And in fact that is used for dilute liquid iron solutions, for example. Dilute solutions of various things in liquid iron uses the Wagner formalism. This is model number 2 in the fact databases, in which the entry, the coefficients that you enter are the log gamma henries. You enter log gamma 2, 0, log gamma 3, 0, log gamma 4, and the interaction parameters epsilon 2, 2, epsilon 2, 3, and so on. But in the FactSage database, the correction terms have been applied. So the FactSage database is not Wagner's formalism, it's the unified formalism with the proper term in here. And again, the cross terms are equal, again, just as it is here. Epsilon ij has to equal epsilon ji when you do the entries. Okay, so the formalism in the fact database is the modified Wagner formalism with the correction terms in. Now you can take Wagner's formalism to higher terms rather than just, you can take this as Wagner's linear formalism, first order formalism. You can have a second order formalism in which you have terms x2 squared, x3 squared, and so on. You can read the paper on. It has the same problems, and the paper shows how that can be corrected as well. I don't think that's all terribly important, but for those of you who are interested, you can read on in this paper and see how the second order and third order Wagner formalisms could be compared to, let's say, Darkens Quadratic formalism or whatever. Alright, so that's Darkens interaction parameter formalism. But you see, the interest is in the physically. The first term, log gamma Henry, is what happens. That's constant and infinite dilution, because when you're taking a huge amount of component 1 and you put atoms of 2 in, every atom of 2 goes into a different environment. In the same environment, so every atom of 2 has the same thing, same energy increment, so you get a constant. If you start getting more and more component 2, then there's a probability that you might find your component, the atom that you enter, might find itself next to another atom 2. In that case, there's going to be an interaction energy, epsilon 2 to x2. Could find itself next to an atom 3, x2, 3, in which case you got x3. This gives you a problem, but if you look at it in the Darkens formalism way with the extra term, you're all set. Okay, any questions about Darkens formalism and interaction, the Wagner's interaction parameter formalism? Okay, for a quiz someday, not next week, I might probably won't ask you about Darkens, but I might ask you something about it. I might give an interaction parameter formalism, because you come across this quite frequently in the literature, especially the old literature. Today, many people are using the Wagner formalism with the correction term, the unified interaction parameter formalism, which is gratifying. Okay. Okay, the Gibbs-Duhem equation. There's your Gibbs-Duhem equation. Page 24. Alright, you can follow this through. But I'm going to write it in a more simple form for you in a moment, but you should read this through. It's pretty clear what's happening. You differentiate equation 70, you compare equations 9 with this equation, and you end up with the Gibbs-Duhem equation that SdT minus VdP plus sigma Ni d mu I equals 0 for any solution. This is a general thermodynamic relationship. No approximation is necessary. Now, what the hell does that mean? That's the generalized one. Let's take the special case. Let's take Tp equals constant. This is the main use that you'd be interested in. Gibbs-Duhem equation. Actually, the Gibbs-Duhem equation, when the mu i's are constant, is the same as the Clausius-Clapeyron equation, and everything is related, but let's not worry about that. Let's take it for the T and P is constant, and then I get sigma Ni d mu I equals 0, or N1 d mu1 plus N2 d mu2 plus N3 d mu3 equals 0 when T and P are constant. That is the Gibbs-Duhem equation that you'll be using. Okay, now how do we, you can derive it as in here, but let me derive it. You have two equations. We have, take a binary solution, N1 mu1 plus N2 mu2. What am I doing now? I'm confused. I'm confused. Yeah, sorry, okay, of course. N1 mu1 plus N2 mu2 equals G. Okay, we know that equation. And we also know that N1 d mu1, sorry, that's one equation you have. that the G is the sum of the partials. The integral is the sum of the partials. Where mu1 is the same as G1, mu2 is the same as G2. We also have another equation, mu1 dn1 plus mu2 dn2 equals dg. dg is a mu1 dn1 plus mu2 dn2. That was equation of thermodynamic. Okay, equation. All right, we derived those two expressions independently way back several weeks ago. So these are two thermodynamic relationships which basically come from the definition of the mu's. So let's take this equation and differentiate it. So if we differentiate this equation, we end up with, well, the differential of mu1 dn1 is n1 d mu1 plus mu1 dn1. So this is mu1 dn1 plus mu2 dn2 plus n1 d mu1 plus n2 d mu2 equals dg. That's simply differentiating that parts. Okay, but you compare that to this expression here. You say mu1 dn1 plus mu2 dn2 equals dg. So that's equal to gt. Therefore, this part has to equal 0. Therefore, n1 d mu1 plus n2 d mu2 equals 0. Okay. The sum of these is dg. That's equal to dg, so that's got to be equal to 0. Okay, so that's the Gibbs-Doom equation. And you can add in the third term, n3 d mu3 plus n4 d mu4. So on, it all comes out to be 0. Now, these two equations, I've done this for G, where mu1 is basically G1 mu2. This would apply to any extensive property, so I can do it for Gxs. I mean, I can write n1 Gxs1 plus n2 Gxs2 equals Gxs. And I can write Gxs1 dn1 plus Gxs2 dn2 equals Gxs, and so I arrive at another, so these two equations here are the same as these two. It's just you replace the total by the excess, and so therefore you get another form of the Gibbs-Doom equation that is n1 dgxs1 plus n2 dgxs2 equals 0. So this can have the Gibbs-Doom equation n1 dg1 plus n2 dg2 equals 0, or you can write n1 dgxs1 plus n2 dgxs2 equals 0. Since you know the gxs of I is RT log gamma I, and you can put that into that expression, and then you're going to get n1 d log gamma 1 plus n2 d log gamma 2 equals 0, which is another form of the Gibbs-Doom equation. Or you can write dg1 as RT log activity 1, so you can write n1 d log activity of 1 plus n2 d log activity of 2 equals 0. Or you can apply this same equation to other properties such as H and S or Sxs. So you can write this for any property. I can write the Gibbs-Doom equation as, I can write the delta H is H1 N1 plus H2 N2, and the delta H is H1 dN1 plus H2 dN2. So then I get the Gibbs-Doom equation that N1 dH1 plus N2, so d delta H1 if you like, d delta H1 plus N2 d delta H2 equals 0, etc., etc. So you could do this. The Gibbs-Doom equation is simply N1 dF1 plus N2 dF2 equals 0, where F could be G, it could be Gxs, it could be log gamma, Fi is G, it could be, Fi could be Gi, Gxsi, log gamma I, log activity of I, Hxs of I, Sxs of I, S of I, any Gibbs-Doom equation applies to any property, okay? You got it. At constant T and P. Clearly you can divide through by x1 plus x2, so you can also write this as x1 df1 plus x2 df2 equals 0, and that's usually the form you find it in. Okay, where F1 and F2 are any total or excess partial property. One mistake that you see sometimes is people try to apply this equation along, say, a liquidus. You measure the activity of 1 along a liquidus, you want to integrate this to get the activity of 2 along a liquidus. You can't do it because the liquidus is not a constant t. This is the Gibbs-Doom equation at constant t and p. This is the overall, this is the, if t and p change, you've got to add those terms in. We don't usually use it in that form. Okay. This is the Gibbs-Doom equation if t and p change. If you have a constant t, if you don't have a, if you're going along a liquidus, you'd have to include this term, which you have to include that term. Okay, so that's the Gibbs-Doom equation. It's a thermodynamic, a necessary thermodynamic relationship. It's not approximate. It's based basically upon the definition of partial properties. One way of looking at what does that kind of mean, it sort of looks just like mathematics. Let's say we're plotting here, this is component 1 and this is component 2, and here I'm plotting some integral property, let's say, I don't know, delta G, delta H. Okay, delta H, then this is the heat of mixing. The heat of mixing will have that expression. Let's just call it F, okay, call it F. F will have delta F, the delta F. Mixing will have that expression, okay. This point here is x2 and x1. This then is f2, this is delta f2, and this point here is delta f1. Okay, and so the Gibbs-Doom equation would be x1 d delta f1 plus x2 d delta f2 equals 0. All right, so that's your Gibbs-Doom expression. Graphically, that's how delta F1, delta F2 are related to delta F. Or, rearranging this, d delta F2 divided by d delta F1 equals minus x1 over x2. Okay? So this is just like a balance, like a teeter-totter. Let's suppose I move this down, I change the slope here, I move this up by d delta f2, and I move this down by d delta f1. I rotate about this point. This end then moves up by d delta f2, this point moves down by d delta f1, and I think you can see that just then the ratio of d delta f2 to delta f1 is the ratio of x1, which is this distance, and x2. As this fulcrum point moves over here, you make a slight change in delta F1, you get a big change in delta F2. If your fulcrum point's over here, it's the other way around. If you were right at 50%, if X1 and X2 were 50%, then the d delta F2 would equal d delta F1. So it's just a lever. That's what it really means. Okay, any questions about the Gibbs-Doom equation? How it's derived and what it means. All right, and this applies, this is for any property, integral or excess works. I said before that Raoult's law and Henry's law are the same law through the Gibbs-Doom equation. Now I can prove that for you. I think it's kind of worthwhile doing. Here's component 1, component 2. This is the activity. The activity of component 1. Like that. Oh, that's the activity. Component 1. And the activity of component 2. So this is the activity of 2. Okay, so what I said was that here, we're taking with this region over here, rich in component 1. Here we have, for the solute, we have log gamma 2 equals log gamma 2 Henry does not equal infinity. That's basically Henry's law. Henry's law says that this limiting slope here is finite. I went through that before. Okay, this is Henry's law, that the limiting value, log gamma 2 And this is as x1 approaches 1, log gamma 2 approaches a constant, log gamma 2 Henry. Log gamma 2 Henry is the limiting slope at x1 equals 1, and it's not equal to infinity. There's a finite limiting slope. Physically, what this means is if you take pure component 1 and you add an atom of component 2, you don't get an infinite change in energy. You just get a slight. And up here we have Réauld's law, and Réauld's law says, not that, you'll often see Réauld's law says that gamma Henry, okay, this is the line here, along this line, here, this is Réauld's line, this is the activity of 1 equals x1. Okay, now you'll sometimes see Réauld's law listed as when x1 approaches 1, the activity equals the mole fraction. But I mean, certainly when the mole fraction equals equal to 1, the activity has to equal the mole fraction simply by definition, not by any law. Just pure component 1 by definition is the point where the activity equals 1. Réauld's law says the slope comes in. Okay. Réauld's law, this line for activity 1 must go through that point by the definition. Réauld's law says it has to come in asymptotically to this Réauld's law line. Okay, so let's take the, how did I write that down here? Let's take x1 d log gamma 1 plus x2 d log gamma 2 equals 0. So that's the Gibbs-Duhem equation in the log gamma form. This is a constant t. So x1 d log gamma 1 plus x2 d log gamma 2 is equal to 0, and I'm going to apply that in this region where x1 equals 1. Okay, so what I have is d log gamma 2 does not equal infinity. That's Henry's law. Okay, x log gamma, so this becomes, so x1 equals 1 and x2 equals 0. 0 times infinity, 0 times anything is 0 unless that anything is infinity. Okay, so this second term, when x2 equals 0, this term is 0 unless log gamma 2 happens to be equal to infinity, but by Henry's law it isn't. Okay, so when x1 equals 1, this second term is equal to 0. x1 equals 1, therefore when x1 equals 1, x2 is equal to 0, d log gamma 1 equals 0. Not log gamma 1 equals 0, but d log gamma 1 equals 0. In other words, it comes in asymptotically. It's the derivative that comes in asymptotically. That's all there is to proving it. Réauld's law and Henry's law are the same thing. Or you can start the other way. If this thing comes in asymptotically, if d log gamma 1 equals 0, then this can't be equal to infinity. The two laws are the same. They're connected by all right, so now what has all this got to do with optimizations and things? Because I'm sure whenever you've done optimizations, when you're doing optimizations, you're curve fitting, you're using models, you've probably never used the Gibbs-Duhem equation. But you haven't been aware. This is like the same thing I said yesterday. When you're doing this stuff, you've got to be aware of what's really going on thermodynamically, and you are using the Gibbs-Duhem equation, even though you didn't realize it. And you can, because you're not realizing it, you can often make a big mistake. And so I want to show you how the Gibbs-Duhem equation applies in these cases. So just like that. And that's what I want. All right, these are the devoir, the homework problems, section 12 on the Gibbs-Duhem equation. Now I'm going to show you a couple of examples from here. The first one, okay, this was very simple for the system. For the system silver chloride, sodium chloride, the following equations for the partial enthalpies have been found in the literature. I say for the liquid, in the liquid phase, you'll find the partial heat of AgCl, you'll find an equation for that in the literature. And for the delta H partial of KCl, we'll find that equation in the literature. The point is, these two equations, this is similar to the Wagner's formalism thing, you can't just write any equation you want for the partial property of one and any equation you want for the partial property of 2. The two are related by the Gibbs-Duhem equation. Okay, so once you have one partial property, the other partial property is basically determined because you can integrate. Okay, if you know one partial property at one composition, then you cannot obtain the other partial property at that same composition. But if you know the partial property of one component as a function of composition, then you can obtain the partial property of the other component over the composition range by differentiation by integration of the Gibbs-Duhem equation. So here's the question. These two equations were given. Are these compatible with the Gibbs-Duhem equation? In other words, is this correct? So we go up here to the answer, and the answer was very simple. There's the Gibbs-Duhem equation. x1 d del h1 plus x2 d del h2 equals 0. Okay, so I made x1 1 minus x2. So d del h1 dx2 plus x2 d del h2 must be equal to 0. So I put my expression for del h1 in this side and differentiate it. I put my expression for del h2 on this side and differentiate it, and in fact it comes out to be 0. So the answer is yes, they're consistent with the Gibbs-Duhem equation. Okay, but this is just to prove the point that you can't just take any expression for one partial property and any one for the other. Okay. Or if you take Wagner's expression for log gamma 2, you can then put that into the Gibbs-Duhem equation and get the expression for log gamma 3, and it is not Wagner's expression unless x1 equals 0, 1. But if you take my unified interaction parameter formalism with the correction term and you do it, then in fact you end up with it. All right, more important one now is number 2, and this is showing you what's going on when you're doing some curve fitting, and this is how we used to do it in the old days when we didn't do things with computers and when you could see more what was going on rather than things being masked by the equations. The activity coefficient of zinc in liquid cadmium zinc alloys has been measured at 435 degrees. So the coefficient of activity has been measured. You can do this by measuring vapor pressures. Activity is P over P0. You can do it in electrochemical cells, galvanic cells, which will measure the various ways of measuring the activity coefficient of one component, or by equilibration with other phases or whatever. The activity coefficient of zinc was measured at 435 degrees and was fitted up to this equation. Log gamma zinc as a function of composition is given by that expression. Okay, this is empirical, experimental. Okay, this is isothermal as well, the temperature is constant, and this applies over the entire composition range from pure zinc to pure cadmium. This is a reasonable form. You see, if the second term was 0, if the second term was 0, it would be a regular solution. The second term makes it a subregular solution. Right. So this is has been fitted up over the entire composition region. Over the entire composition region, and now the question was then, what is the question? Right, and true, find an expression for log gamma cadmium for the other component as a function of composition at the same temperature. So if you have measured log gamma zinc over the entire composition region as a function of composition, and expressed it up like this, you can now integrate that in the Gibbs-Duhem equation and you can obtain log gamma cadmium. If you measure log gamma zinc over the whole composition region, you can obtain log gamma cadmium. Okay, now you might do this if you were using fact stage. You put this thing into the polynomial model, you fit up log gamma cadmium, and you put this into your least squares program or whatever, and you obtain this. Okay, then fact stage will immediately give you the log gamma cadmium and give you the integral properties and everything. But what is it really doing? What's really happening there? You're fitting this into your equation. So let's look back to how you would do this if you were going to do this back in the days when you had to integrate things graphically somehow. All right, so basically here we're going from zinc to cadmium, and log gamma zinc, this would be equal to 0, and log gamma zinc is going to have some sort of an expression like that. Okay, when x cadmium is 0, log gamma zinc is 0, and then log gamma zinc is going to go over to okay, so we're going to put this into the Gibbs. This expression is going to go into the Gibbs-Duhem equation, and we're going to integrate it. All right, so I have two ways of doing this. The first way is the one I think we should look at. All right, so there we have X cadmium d log gamma cadmium plus X zinc d log gamma zinc equals 0. So this first expression, and this is your Gibbs-Doom equation. Okay, so now I'm going to integrate the Gibbs-Doom equation, and I'm going to, when you do an integration, you have to take the integration from a lower limit. So my lower limit is going to be here, at this point here, where the mole fraction of cadmium equals 1. This is my lower. I'm integrating from that point back. Okay. So I'm taking the integral. So I put the X cadmium over on the other side with a minus sign here, making it equal 0. And so this is rearranging the equation, and I'm taking the integral from X cadmium equals 1 on both sides up to any arbitrary composition that I want along here. Okay. Now here, this is d log gamma cadmium going from, you might want to write an upper limit X cadmium or X zinc on the two sides. Okay, the left-hand side of the equation, I wrote log gamma cadmium. How can I do that? The integral of the left-hand side is log gamma cadmium at X minus log gamma cadmium at X cadmium equals 1. Equal. Okay, that is the left-hand side. If you integrate d log gamma from X cadmium is 1 to X, you get log gamma cadmium at X minus log gamma cadmium at your integration limit. But I chose the integration limit as X cadmium equals 1 because when X cadmium equals 1, log gamma cadmium equals 0. By definition. Pure material, the gamma is equal to 1. So this term here equals 0. Okay, so I've taken my lower limit of integration. When you're doing an integration, remember, this is a differential equation. I have an expression for log gamma zinc, which I'm given. I'm trying from the differential equation to obtain the expression for the corresponding expression for log gamma cadmium. In a differential equation, you can always calculate this other function within a constant of integration. But there's always going to be a constant of integration when you solve a differential equation by integration. In this case, the constant of integration is log gamma cadmium at the lower limit, where we happen to know it. So you have to know, you're solving a differential equation, you need the expression for log gamma zinc as a function of composition, and you need one value of log gamma cadmium at some point in order to obtain the constant of integration. Okay, so we pick a point where we know the activity coefficient of cadmium, and then this is our constant of integration. Okay, then I integrate the right side of the equation. I differentiate, put in here d log gamma cadmium, I differentiate this from X cadmium equals 1. I do the, take the definite integral, you can go through my mathematics, and you end up with this expression, which I rearrange. X cadmium is 1 minus X zinc, and I obtain my final expression for log gamma cadmium. Okay, so log gamma cadmium is given by that expression, and that corresponds to the expression. Okay, so I have an expression for log gamma zinc, which was given. I then integrate the Gibbs-Doom equation, which is a differential equation. I need one value of log gamma cadmium at some point where it's known, so I pick the point over here, X cadmium equals 1, it's known, so that's 0, and then I can solve to get the whole thing. Okay, remember this can only work at constant pressure, constant temperature and pressure. One mistake people make, we talked the other day, say I have a phase diagram, temperature versus composition, and I said over here along this liquid is here, if you know that there's no solid solubility, you know the heat of fusion, you can obtain log gamma 2. Log gamma 2 can be measured along from analyzing the phase diagram. Okay, you got, RT log activity is 2 is minus the heat of fusion of 2 or minus T over T fusion. You can get log gamma 2 along the liquidus. You say, okay, I got log gamma 2 along the liquidus, I can now integrate my Gibbs-Doom equation to get log gamma 1. No, you can't, because this is an isothermal. Okay, it's got to be isothermal before you can integrate it. Okay, so suppose, however, so that's fine, and that's how you would integrate it, and that's what's really sort of going on. Now the computer isn't doing it that way. In the computer, you're taking the expression here for log gamma zinc, it's writing out the equivalent integral property expression and going back, but it's integrating the Gibbs-Doom equation. You put this into fact stage. If you put this into fact stage, you're going to get exactly this answer for log gamma cadmium. All right. Suppose now, this is the problem that you run into when you are doing the thing in the computer and you're not doing it graphically or looking at what you're doing, is let us suppose now that our experimental measurements for log gamma zinc did not extend over the whole composition region, but in fact only extended up to 40–50%. So now I fitted up the equation. My equation here for log gamma zinc that I gave you has been fitted over this composition region. Right? But the rest of it is simply an extrapolation of that cubic equation. Okay. Okay, so if the composition rate, you can still fit it up, and this is what would happen. I could still fit this equation here over this composition region. So my experimental points will end somewhere here at 50%. I fit the experimental points up to this equation. That's fine, but that equation clearly only applies over that range. And the rest of it down here is simply a mathematical extrapolation. But now when I integrate the Gibbs-Duhem equation, I'm using this as my endpoint. I need my constant of integration. The constant of integration is based upon the fact that log gamma cadmium equals 0 at pure cadmium. Okay, so what I'm doing is I'm using this endpoint here, the value at this endpoint, in order to use my constant of integration, but that's based on a long extrapolation of the experimental data. You're not really justified in doing that, unless you really believe that the equation that you wrote here is this extrapolation is good. When you're looking at it this way, when you're really looking at the integration, you're basing your whole thing on a really invalid extrapolation. You don't have your constant of integration. You have all the other terms, but you don't have your constant of integration. Okay, so what you're going to get is you're going to get log gamma cadmium. Let's just look at the same thing then. The log gamma cadmium looks like that. You've taken your log gamma zinc, and then you've integrated it from this point and to give you your calculated curve for log gamma cadmium. If your experimental data really go over to that point, then everything's fine and you can calculate the thing. But if your experimental data only go over to this point, then your log gamma cadmium, the slope and everything here is correct, but you could be off by a constant. So the solution of the differential equation is a family of curves. Log gamma cadmium, family of parallel curves over here, which differ by the constant of integration. Only if you're sure that this thing extrapolates all the way to here correctly are you going to get the right curve over here. Otherwise, you could get a different curve. Is that clear what's that? Your constant of, now, if you'd have to know, if I knew log gamma cadmium at some point in this region, say I know the activity of log gamma cadmium at this composition where my experimental data end, then I would know, well, that's the curve that I'm using over that region. But I need somewhere within the region of composition where it's been measured, I need one value of log gamma cadmium in that region where the log gamma zinc has been measured in order to fix my constant of integration. Now you might know that from some other value, for example, but okay, so for example, let's suppose we had it this way. This will be, let's see, this will be zinc and this will be cadmium. Supposing the diagram looks like this, obviously it may not. Let's suppose you measured log gamma zinc. These are your experimental points at constant temperature. Log gamma zinc has been measured over this composition region. Now I can integrate the Gibbs-Duhem equation to get log gamma cadmium over that composition region, give or take a constant of integration. But now I know that at this point I can use this composition. If the liquidus composition is known, this is X cadmium on the liquidus, I can use this at this point, I know that log gamma cadmium, at least with respect to the solid standard state, equals 0. So I can then obtain the activity of, I can integrate the Gibbs-Duhem equation to get the activity coefficient of cadmium over this region using the one known endpoint value here, because I know that on the liquidus it's in equilibrium with solid cadmium. So the activity coefficient with respect to solid cadmium is 0, and if I know the heat of fusion of cadmium, I can correct for the standard state change, or if you like, the other way of looking at it is if I know the heat of fusion of cadmium, the other way of looking, same thing. If I know the heat of fusion of cadmium and I know this liquidus composition, then I can solve my RT log gamma equation to get the activity of cadmium here, so that becomes my endpoint. Okay, but I'm using this endpoint. Right. And then my log gamma cadmium, again, only applies strictly over this region and does not apply down to that region. Okay, so you see that when you're doing this, you have to look at what range has my log gamma zinc been measured, and my log gamma cadmium then is really only known over that region, give or take a constant of integration. I might have some known value of log gamma cadmium in that region, which permits me to fix my constant of integration, or I might not. If I don't, I can extrapolate this thing all the way over to pure cadmium and use this as my endpoint, but then I'm basing the whole thing upon an extrapolation. Now, when you do this in the computer, though, you give the computer automatically kind of uses this endpoint value. So if I put this into and I say I give this equation for log gamma zinc, the computer's going to put this automatically in because automatically extrapolated is going to give you this expression for log gamma cadmium. Okay, and you say that just looks wonderful, but there's a hidden thing in there. The hidden assumption is that that equation for log gamma zinc applies over the entire composition region, and if it doesn't, then this doesn't apply over the whole composition region. But you can lose this, and you see this a great deal in the in the literature. In fact, you see it an awful lot. And this is what you generally see. Let me show you. Let's say you have a simple phase diagram, 1, 2. And we analyze, let's say we analyze the system to get log gamma 2 along this liquidus, as we did from the equations. Log activity of 2 is 1 minus h of fusion, 1 minus whatever. You get the activity. So over this region we have gamma 2 over this region from here to here, and from here to the eutectic temperature we can calculate gamma 1. So gamma 1 is obtained from the phase diagram from pure 1 to the eutectic. Gamma 2 is obtained from the phase diagram from pure 2 to the eutectic. Now, you can't integrate the Gibbs-Duhem equation strictly because you don't have a constant of integration. You don't have the, it's not isothermal, but if we know the heat of mixing, say the heat of mixing is known, then as we did in the problem, I think 13.3 or something, you can integrate these things up and you can obtain, you can integrate up using the delta H. You can take the log gamma 2 at this temperature and move up to log gamma 2, right? Okay, so as we did, I think it was a cadmium something, bismuth cadmium system, 13.3 I think. We had log gamma 2 from the liquidus, we knew the partial heat, so you could get log gamma 2 at a higher temperature. Or if you're assuming, for example, that the excess entropy is 0, you're making some sort of assumption, anyway, to render your gamma 2's isothermal. So let's say we have the heat of mixing is known, so the partial heats of mixing are known. So you get gamma 2 on the liquidus, you then go up using your partial heat in the Gibbs-Helmholtz equation, and you end up with, basically, gamma 2 over this region, and you end up with gamma 1 over that region. Now, you've got gamma 2 over this region, you've got gamma 1 over this region. Okay, so what you've got then is you have gamma 1 and gamma 2 are both known at this point. Okay, so now you're okay, because you're using this point as an endpoint for the integration of gamma 1 and using this point as an integration. So you're integrating both the Gibbs-Duhem equation, you're using the value of gamma 1. The Gibbs-Duhem equation on this side gives you log gamma 1 over this range within a constant of integration, but you can calculate the constant of integration because you know gamma 1 at that point. Okay, and here you have Gamma 1 is known over this region. You integrate the Gibbs-Doom equation to get gamma 2 over this region. And since you know gamma 2 at that point, that gives you your constant of integration and everything's fine. So if you're doing it this way, you have both liquidus curves here. You've got the thing up isothermally and so on. Then when you do it in the computer, or you do it, this is equivalent to what's happening. And then you're okay. Now you see that the whole thing was known. You had, this liquidus only gave you gamma 2, but you do have an endpoint here from this liquidus, so everything's okay. So you can see that what you're doing is correct. But in many cases, when you're fitting up phase diagrams, in many cases more often than not, you probably don't have too much over here. You do have a liquidus over here for component 1. So your liquidus for component 1 gives you gamma 1 over that region. Now you're doing the same thing as I did over here. You're getting gamma zinc over this region, fitting it up to an expression, and that expression gives you log gamma cadmium. But that log gamma cadmium isn't strictly correct because you don't have the endpoint. But you don't see that. Okay? You don't see the fact that you don't have the endpoint. You've only measured this is zinc and this is cadmium. You've only measured it up to here. And yet you're then saying that fine, that liquidus here has permitted me to get log gamma cadmium by, okay, so you fit your log gamma zinc up expression from here, and then you get log gamma cadmium from this, but it's wrong. You got a plus constant, and you don't know that constant because you don't have the log gamma zinc all the way to the end. So remember that if you have a phase diagram and you're just using the liquidus up here, that liquidus gives you the activity coefficient of the solvent. Okay. If you then fit that up to an equation and you get the activity coefficient of the solute, and you don't have any other data to fix the endpoint, then you're getting something that is, the slope might be right, but you don't really know the actual value. And you see this all the time. An example, aluminum calcium. The liquidus here has been measured, and you fit up the liquidus beautifully, and you get a lovely value for the excess for the activity of aluminum, which is the solvent, close to 1. And you find out that the gamma calcium is very, very negative, but the gamma calcium isn't really fixed. It can be off by a huge amount, okay? Because you're not fixing an endpoint anywhere. Even if you do have the endpoint fixed, remember, even if you did have an endpoint fixed over here, okay, now you can integrate, but remember you are integrating. So let's say you do have an endpoint fixed over here, so we're integrating from the endpoint back here in order to get the activity coefficient of cadmium. You're still integrating a differential equation. The further you go away from your endpoint, the less accurate it is. Okay, if you fit up this liquidus, say it's the zinc cadmium system, you fit up this liquidus, it's giving you the activity of zinc over this region. The equation you get to fit up the activity of zinc then is accurate because it's going through actual experimental points. If you then use that same expression to give you the expression for cadmium, x cadmium, using say even a known endpoint here, or even if you know it all the way over to pure cadmium, you're integrating away from your endpoint towards this end, and the further you integrate, you have cumulative errors when you're integrating an expression. Okay. The log gamma cadmium, you're solving a differential equation, so the log gamma cadmium, okay, you're taking the slope of this log gamma zinc and you're integrating that slope all the way from one end to the other. The further you go, the more cumulative error you have. Okay, so in the aluminum calcium system, even if you do have a reasonable endpoint, you can't expect, as if you haven't measured the calcium activity exactly, it can be really quite far off. And it can be quite sensitive because if you look at this, it depends upon the activity of cadmium depends upon the slope of the gamma zinc curve. Okay? So it isn't important when you're fitting this curve, the equation, the experimental data. You fitted the experimental data to that function, to that expression, so these are your experimental data. But when you're integrating to get log gamma cadmium, even when you have the proper endpoint, okay, it's not the actual values, it's the actual slope that's being integrated. So this is not highly accurate. You have to know the actual data points for log gamma zinc might be quite accurate, but the slope is far less accurate. Okay, so remember what you're doing. What actually was measured? Was it log gamma zinc? Was it log gamma cadmium? What was measured? And remember that even if you're then calculating the partial property of the other component, you need the endpoint, or else it's undetermined. But even if you have the endpoint, the partial property of this other component is not going to be as accurate as the partial property of the thing that was measured. and sometimes it's way, way off. And this can actually be one last thing before we have the break. Okay, it depends on the slope, but the slope now is very, very, say you measured log gamma zinc. We're doing this thing now, the endpoint's fine. We measured this thing over the entire composition region. We're integrating back here to get log gamma cadmium. It depends on the slope of this curve of log gamma zinc. Now, as you approach pure zinc, the slope is almost zero because you're in the Rayoltian region. So the slope only varies very slightly over a composition region here. But if you look at the Gibbs-Duhem equation, that very slight change in slope has a really big effect on log gamma cadmium, because it is in this region. In this region up here, log gamma zinc varies very slightly with composition. So we do this whole thing, we do it kosher, and you end up with this expression. So this is your log gamma cadmium coming down to here. Okay, so I've taken the zinc curve, this is my experimental point, I've integrated, and I get the log gamma cadmium. But the slope, the Gibbs-Duhem equation relates the slope here to the slope here. A very small change in the slope here can have a huge change in the slope here, because the log gamma cadmium be log zinc. And the Gibbs-Duhem equation, log cadmium is log zinc, is x cadmium over x zinc, that goes to infinity. So what happens then is that these could be really quite accurate measurements of log gamma zinc, but since the slope is almost zero, because it's almost going into zero, very slight errors here can have a huge effect on this here. Okay. And that's something else that kind of is masked when you're just leaving the equation. So you got to really think about what is happening. So effectively, this is what the computer is doing. And you've got to have really accurate measurements of this liquidus of aluminum. Even if you have a proper endpoint for calcium, if you're getting the activity of aluminum from the liquidus, okay, any slight errors here are going to have a really big influence. Okay. And you find that this is important, the activity coefficient of calcium, if you look at the literature from different measurements of the activity of aluminum, can vary by like 3-4 orders of magnitude, which is rather important. If you're making aluminum, you're worried about calcium vapor pressure and so on. The only really good way to get it is to actually measure the activity of cadmium, not the activity of the other thing, and then differentiate it. Okay, so sometimes you look at an optimization of a phase diagram and you say, this phase diagram is beautifully optimized, so therefore it must be right. I get the aluminum calcium system, it just fits the aluminum liquidus beautifully over here, so my activity of calcium has got to be right, but it doesn't. Any slight change in that liquidus could have a huge effect on you. Okay, you've got to be careful. So think about the Gibbs-Duhem. Great, I'm going to give you some homework problems with the Gibbs-Duhem integration using equations and graph paper and so on, so you get an idea of what is actually happening when you do the optimization. I can't stress this enough because this is really important. You see all sorts of problems with optimizations and error limits. And this is why you can see an optimization that does a beautiful fit to the phase diagram and maybe a beautiful fit to some of the thermodynamic properties, but that doesn't mean that every partial property, every vapor pressure is going to be accurate. Which ones were measured, which ones were calculated by differentiation, which were calculated by integration. Those that are calculated by integrating a differential equation, the further you get from your endpoint, the worse it is. This is a notoriously dangerous thing to do. Okay, so I've made my point. Okay, let's take a nice long break here. Oh, God. Why have I got 3 of these things here? Okay, 1, 2, 3, go.